Um, okay, we are hearing from Sojo Shimamori-kun from Osaka University, and he will talk about the non-invertible symmetries in non-rational conformal field theories. Let's start.
Thank you, introductions, and thank you for inviting me to this conference. So my name is Sojo Shimamori, and I'm a student at Osaka Universities. So today, I'd like to talk about non-invertible symmetries in non-rational conformal field theories. So also, this talk is based on the joint work with Yuta Nagoya and last year's paper. So firstly, let me begin with introductions. And generalized global symmetry can be associated to the existence of topological defects. And as a branch of generalized global symmetries, in recent years, non-invertible symmetry has been widely studied in various dimensions. So these are partial lists of non-invertible symmetries. And historically, non-invertible symmetry has been widely discovered in rational conformal field theories. So rational CFT is two-dimensional conformal field theories with some extended chiral algebra. So by definition, the number of irreducible representations of chiral algebra is finite. So the most prominent example is Wiemann model and Westman-Witte models. So I want to explain the non-invertible structures in rational CFT. So in rational CFT, we have a primary field, which is denoted by phi k, and k represents some irreducible representations of chiral algebras. And then we have this kind of fusion ring. So then there is one-to-one correspondence between this primary field to this firing line. So this firing line satisfies these fusion rules. So I have some comments. And the first one is this fusion algebra is finitely generated. So this is just the definitions of rational CFTs. And from this, we can understand that non-invertible symmetries ubiquitously appear in rational CFT. So the central question of this talk is as follows. So how about non-invertible symmetries in non-rational CFTs? So the landscape of conformal field theories is so vast. And as I said in the previous slide, the symmetry structures in rational CFTs are very understood. But on the other hand, for non-rational CFT, it is so mysterious to understand the fusion structures. So today's my talk is the fusion structures in non-rational CFTs. But of course, it is quite hard to give a complete answer to that question. And so in this talk, I will mainly focus on C-core2 bosonic truss CFT. So this is the main actions which will be treated in my talk. And the main goal of this talk is to explain the fusion structures of this model. And as a main tool to review the fusion structures of this model is half space gauging. So in the next few slides, I will give a review on half space gauging. But before that, I have one comment. So we can also include the topological term into this action. But in this talk, I do not take into account that. And this, after submitting our paper, then there is some interesting paper which is written by these authors, appeared. And in this paper, the effect of topological term is also discussed. So if you are interested in the effect of topological term, then please see this paper. So these are today's my outline of my talk. And firstly, I present review on half space gauging. And in the rest of sections, I'd like to talk about our work. So the assumption is like this. So suppose there is a global discrete symmetry H0 in theory TG. So here G means coupling, which characterizes theory. So when we nicely tune the coupling G to some value G star, then the theory is invariant under gauging. So namely, this gauging invariance can be schematically written like these equations. So in the next few slides, I give some concrete examples. So I firstly consider the C=1 compact ozone model, and the non-invariant structures of this model was developed in this paper. So its action is pretty simple, and R serves as a role of parameters characterizing the theory. So we focus on this CN shift symmetry, which shift the compact boson like this. And then the charged object under this shift transformation is vertex operator, which is written like this. So here, of course, the charge of vertex operator takes only integer values. So in this model, there is a T dualities. So namely, the theory with radius R is equivalent to the theory with 1 over R. So this is the key properties of this model. So we now show that when this compact radius R is tuned to be square root of n, then the compact ozone model is invariant under ZN shift symmetry, ZN shift gauging. So we will check this by seeing transitions of the charge lattice under gauging. So this is the charge lattice of this vertex operator. And as a result of gauging at the end shift symmetry, then these are possible charges. So to bring this charge lattice to the original one, we must perform the rescaling to this charge lattice. And then we can completely realize the original lattice. So this is equivalent to, in the previous slide, we saw that the transitions of charge lattice, but its transition can be translated in terms of this compact radius. So namely, as a result of gauging the shift, this compact radius is mapped to this value. So this implies that TR over Cn shift is equivalent to TR over N. So moreover, by combining T dualities, So recall that T duality maps as a compact radius to its inverse. So this theory is equivalent to this theory. So if we tune this compact radius to square root of n, then this relation is established. So I stress that this gauging invariance implies the existence of non-invertible symmetries. So I next explain the construction of non-invertible symmetries. So this construction needs two steps. So the first one is to introduce an interface and gauge some discrete symmetries over the right regions. So we next tune the ball coupling G to G star. So now we assume that this theory is invariance and gauging when the ball coupling is tuned like this. So in this setup, this red line becomes an interface in a single theory. So the examples of C equal 1 compact boson model, this interface can be written as a form of defect action like this. So now we decompose the spacetime into left and right regions. And correspondingly, we have the left compact boson and right compact boson, which are located in each side. So by using these fields, we can construct non-invertible defect. And now we have a Lagrangian form. Now we can write this non-invertible defect in the form of Lagrangian. So from this, we can calculate the fusion algebra of this theory. So this is a result of the computations. And this fusion algebra is often called Tambara-Yamagami categories. And in particular, this fusion algebra is commutative because this commutativity can be seen from this fusion rule. So we next proceed with our work. So namely, our target model is this C equal to bosonic torus CFT. So now we apply half space gauging and explore non-invertible symmetries in this model. So unlike in the C equal 1 case, we have many global symmetries. So the two different kinds of shift symmetries and two winding symmetries. But in this talk, I only restrict ourselves to the half space gauging coming from these shift symmetries. And then the charged object under these shift symmetries can be written like this vertex operator. So now, of course, this charge vector takes only integer values. So the charge lattice can be written like this form. And to perform the half space gauging, we must choose a discrete subgroup of this product shift symmetry. But unlike in the C equal 1 case, we have many choices as a subgroup. And in this talk, we particularly choose these two kinds of discrete subgroup. And the first one is product group, and the second one is diagonal subgroup. Each transforms a vertex operator like this. So in the same way as C equal 1 case, as a result of gauging this discrete subgroup, the charge lattice is projected out. So as a warm-up, we start with the gauging this product subgroup. So as a result of gauging this product group, this charge lattice is projected onto this invariant state. And for later convenience, it is also convenient to introduce these two vectors, which characterizes the charge lattice. So we denote these two vectors by L1 and L2. So for later convenience, we put these two vectors into the single matrix K. And in the product case, this matrix is this diagonal form. So this is just a double copy of a C equal 1 case. So in order for this lattice to be brought to the original one, we must perform the rescaling the same way as C equal 1 case. But when we next consider this diagonal subgroup, then the situation is drastically changed. So the gauging this diagonal group means only invariant vertex operators under these transformations survive. So N1 plus N2 is 0 mod 2N. So in this case, we can also prepare these two vectors, and we can put these vectors into the single matrix K. So unlike in the product case, in this case, this charge matrix is not symmetric in this case. So this fact is very crucial in later discussions. And in this case, we must perform not only rescaling, but operation of rotation is needed. So namely, first, we rotate this charge lattice such that this line sits on the first axis. And after rotation, we must perform rescaling. Then this charge lattice, after gauging, is brought to the original one. So this rotation is unique to diagonal subgroup, and this is not necessary for a product group. Yeah. In that case, in that case, we firstly rotate this parallel such that, like this, and then performing some operations and bring to this form. And after that, we need to rescale. So we need another operation in that case. So also in this case, we can translate such a transitions of charge lattice can be, that transitions of charge lattice can be translated in terms of the coupling. And so as a result of gauging H, then this coupling is mapped to this one. And so then we use duality and we map this coupling to its inverse. So in this case, in order to realize the gauging invariance, we must impose these self-duality conditions. So let me summarize so far. And matrix K carries full information of gauging H. And in the C equal to case, we have many choices in discrete subgroup. And the theory is invariant and gauging H when the coupling is tuned to satisfy these self-duality conditions. So this is a summary so far. Yeah.
Self-duality means that the partition functions are the same on torus.
Yeah, yeah.
But what about sphere?
So in our case, sphere, the space-time manifold is sphere.
What about G-ring surface?
Oh.
I mean, I'm just referring to the fact that it's known that the Taylor is generated.
Yeah.
Duality.
Yeah, yeah.
So you get a different Euler counter curve, and the partition functions don't actually agree on curve manifold. So is it still self-duality, or there is some sort of anomaly?
So are you saying the existence of diatom when we consider the general Riemann surface? Yeah, yeah.
I was just asking, so is Zohar asking about the target space being something more general or the world sheet?
So
What was the question?
yeah, now we restrict the target space, space-time to the R2, and we do not consider the general Riemann surface. Yeah.
Yeah, I think there still is a non-invertible symmetry, you can say, but that doesn't give you, that doesn't say that the partial function is equivalent on the general G image. There is a it's not invertibility. Yeah. Yeah. Okay, go ahead.
Okay, thank you for questions. So next, it is natural to ask that couplings are satisfying these self-duality conditions are rational or non-rational. But we can now exactly solve the self-duality condition, and its solution can be written like this form. And so here, D is defined like this. And in physical system, it is quite natural to impose this coupling to be real. So this implies that this D must be negative. So this is a result coming from the physical conditions. So our interest is this solution rational or non-rational CFT? So to classify them, it is convenient to introduce these two moduli. So here, tau is the complex structure modulus, and rho is a complexified Kähler modulus. So now, by substituting this cellular solution to this value, then tau star satisfies this kind of quadratic equation. So this means this complex structure modulus belongs to the quadratic imaginary field. So now I require this discriminant to be negative. So in this case, this is exactly quadratic imaginary field. So and the reason why I introduced these moduli is just to use Goff-Buffer's argument. So based on their argument, when both moduli belong to the same quadratic imaginary field, then the corresponding CFT is a rational CFT, and its reverse direction is also true. So this is the Goff-Buffer's argument. And by using this fact, we can show that when K is symmetric, then the corresponding CFT is rational. But when K is not symmetric, then the CFT is non-rational. But we have seen these examples so far. So namely, when H, when we choose this product group as a H, then we should recall that the matrix K is diagonal. So in that case, the corresponding CFT is rational. But when we consider this diagonal gauging, then the corresponding K matrix is not symmetric. So if we choose this subgroup, then the non-invertible symmetries become emergent at non-rational points. So I'd like to next explain the construction of non-invertible duality defect. So far, we saw that the theory is self-invariant when we tune this coupling like this. So in this case, we can construct the non-invertible symmetry defect associated with this gauging. So its action can be described like this form. So here, in the same way as C equal 1 case, we split the space-time into left and right regions, and we prepare two kinds of compact bosons. And then the non-invertible defect can be described by this defect action. So here, as a coefficient, as a matrix K appears. But this is quite natural because the matrix K carries informations of gauging. And so we can successfully identify the non-invertible symmetry points. And so we next consider we next calculate the fusion algebra. And in this talk, I will explain the fusion structures concerning these two defects. So the first one is, of course, non-invertible symmetry defect. And the second one is H symmetry defect. So here, the vector P must satisfy these gauging conditions. And in the rest of talk, we will only consider this diagonal gauging. So in this case, the vector P is chosen like this. So let me begin with a fusion eta P times D. So in this case, this fusion picture can be schematically drawn like this. So namely, we bring this H symmetry defect from the left. And the effective defect action is written like this. And after changing proper integral variables, then this effective action can be transformed to this form. But now we take the summations over I. So in this case, by using this gauging condition, this coefficient is 0 mod 2n. So this last term becomes trivial. Yeah.
Each tick generates global transformation with which you gauge the.
Yeah. So in this case, the last term is trivial. And so the remaining defect is non-invertible symmetries. So from this, we can obtain this fusion rule. But when we bring this H symmetry defect from the right, then some different situations occurs. So this is the effective action. And after changing integral variables, then this effective action can be mapped to this one. But and the second term is nothing but the non-invertible defect. And we should focus on the last term. So unlike in the previous case, now we assume over, now we take summations over J. So by recalling that gauging condition, in this gauging condition, the summation over this part, but now we take summations over here. So this means that when the matrix K is symmetric, then we can flip these indices and we can use the gauging condition. And this last term becomes trivial. But when K is not symmetric, then this last term becomes non-trivial Zn tilde winding symmetry defect. So here, n tilde is defined by 2n. So namely, by recalling that when the conformal field theory is non-rational, then this condition is satisfied. So this is a major distinction between rational and non-rational conformal field theories. So this is a summary of the fusion rules in non-rational CFTs. So now we bring this H symmetry effect from the left, then it can be absorbed to this non-invertible defect. But when we bring this H symmetry effect from the right, then non-trivial Zn winding symmetry appears in the left side. So it is natural to ask if when we bring this emergent Zn winding symmetry from the right, then what happens? So this is a result of the fusion. This is a result of the calculations of fusion rules. And the first one is again non-invertible symmetry effect. And please look at this last one. So we can show that determinant k is always 2n. And so the extra factor of 2n also come from this inverse matrix. And so this last one represents the Zn tilde squared shift symmetry generator. So this fusion rule can be schematically written like this. And we can proceed this analysis, however. And so this is a total summary of the fusion rule. So when we bring this shift symmetry from the right, then this winding symmetry appears. And when we bring this emergent winding symmetry from the right, then this shift symmetry becomes emergent. So this implies that in non-rational CFT, infinite number of topological lines contribute to the fusion algebras. So this is the major distinctions comparing to the non-rational case, rational case, because in rational case, it is enough to finite number of topological line defect in order for the closure of algebras. So finally, I'd like to explain the closed fusion subalgebra in non-rational CFTs. And so far, we have seen that the fusion algebra in non-rational CFT is infinitely generated because there is an infinite tower of shift and winding symmetries appear. But even in that situation, we can find out a closed subalgebra in the non-rational case. So to see this, we should note that there is an emergent Z2 symmetry at self-dual point. And we firstly note that this self-dual condition is equivalent to this one. So this can be easily shown. And this equivalence implies that there is some Z2 symmetry which maps the matrix K to its transpose. And indeed, this symmetry transformation can be realized by the transformations acting on this compact boson field. So here, this representation matrix is written like this. And this matrix satisfies these three conditions. So this matrix does not change as a value of coupling. And if we sandwich S and ST, then the K is mapped to its transpose. And by introducing dressed duality defect and projection defect like this, we can find some closure algebras, some closed algebras. So here, D hat S1, S2 is defined by this. And the last one is the symmetry defect with respect to emergent seat symmetry. And DS2 is defined like this. So here, the first one is nothing but ordinary non-invariant defect. And the last one is dressing winding symmetries to this non-invariant defect. And we can also introduce this kind of projection defect. So now these two parts correspond to the dressing term. So then by using these dressed topological defects, we can obtain these closed subalgebra, even in the non-rational case. So from this algebra, we should note that D times C is not equivalent to C times D. So this means that this non-invertible fusion algebra is non-commutative on the non-rational case. So let me finish my talk by summarizing. And we explore non-invertible symmetries in C equal to bosonic torus CFT by using half-space gauging. And in particular, we discovered non-invertible symmetry defects are not only rational, but non-rational CFTs. And we also explore fusion structures in non-rational CFTs based on the half-space gauging. So we have a lot of future works, but these are just two of them. And the first one is exploring dynamical constraints. For example, the string theory, because in string theory, we often have a C equal to conformal bosonic torus CFTs. And the second one is to interpret our fusion rule from the perspective of symmetry TFT, symmetry TFT. So that's all. Thank you so much.
Thanks for the very nice talk. Is there any question?
You consider the cubic lattice in the setup. Cubic. Sorry, so, rectangle lattice.
Yeah.
Can we consider triangle lattice, for example, instead of the rectangle lattice?
triangle one?
Instead of the rectangle lattice, can we consider triangle lattice in the setup?
Sorry, what do you mean by triangle lattice?
Tra- uh, ah, this is called only uh, uh, and
The question is that whether you can turn on the button, the B.
B.
Magnetic
B.
B field. Are you saying that what happens if we turn on the B field?
B.
Mm.
V. Yes.
No. If we turn on a B field, then we can shift charge lattice by some angles. In that case, we can also consider that. But now we restrict our case to the case where there is no B field. So in that case, we cannot achieve that.
Sorry, I do not familiar with B field, and B means V.
No.
B. Yes, angle is even now 19 angle. Ever B.
Yeah.
Yeah.
Mm.
We should add the term.
Yeah.
I see. Not B field is for simplicity or cannot add.
Yeah. So the main goal of this talk is to see what is the fusion structures in non-rational CFTs, and so I restrict to the case where there is no B field. Yeah.
Add the B field is allowed.
Yeah.
Thank you.
Yeah. So if we turn on the B field, then some discussions are performed in this paper.
Thank you.
Any other questions? We have plenty of time. Would you elaborate on the SimTFT perspective? Do you have anything in your mind that how to do this this kind of?
Recently, the non-invertible symmetries in C=1 case, then the symmetry TFT perspective arise in the paper. So I think it is natural to extend such work to C=2 case. But yeah.
And do you have another question from me is that do you have any into the understanding of why you get this finite the invertible symmetry closed on the finite?
That's good questions, and I also consider that, but I cannot have a satisfactory answer to that question. Yeah. So after some trial and error, we can find this dressing works well, and it is not clear to me the deep physical interpretations of this dressing. Yeah.
Is this some known like fusion category that appears everywhere, or like in some small n case, or like is it?
So firstly, I suspect that this closed algebra is some graded algebra, but
Yeah.
this additive property is not does not match with credit case, and so I also leave the mathematical interpretations of these future algebras for the future work. Yeah.
Thank you. Any other questions?
How about when we consider the invariance under twist gauging?
So
For example, take GN, it's subgroup of U1, one of the U1 shift, and another GN, it is also subgroup of GN, then we can consider the twist gauging, right?
so
Because
I haven't considered that. So let's discuss after
okay.
the seminar. Yeah.
Any other questions?
I have a microphone. So in this talk, you told us how to obtain via half gauging one type of non-invertible symmetry, which comes from one particular element of the T-duality group,
Yeah,
which
yeah.
is the one that inverts the entire metric.
Yeah, yeah.
Do you know what you would have to half space gauge to get the non-invertible symmetries corresponding to the other elements of T-duality?
For more generic T duality case, right?
Right.
Yeah. So now we used used the duality, but this is not the fundamental ones. So in the C=2 case, we can have more fundamental duality transformations, and so we can of course use such a fundamental duality transformations and obtain the non-invertible result.
I guess you have to find a certain subgroup that you gauge to undo that transformation, right?
Sorry.
To construct a non-invertible defect, you want to find some subgroup that you gauge that you can then undo with that particular element of the T-duality group. So do you know what that subgroup H would look like? It wouldn't be the diagonal one anymore. It would be some other thing you have to gauge. Do you know?
So after this talk, let's discuss here.
Okay, sounds good. Thank you.
Okay, any other questions? Okay, if not, let's thank speaker again.